Hello everybody. I decided to record a bonus clip for the instantaneous power because this is covering a more in-depth than what the text did. So this is going to be a extra credit if you're taking the class and watching this video. This is going to be extra credit for watching this video. So this is not required, but I think it's good to know if it will be helpful in terms you have broader, more insightful view of the things. Let's look at the more general case. Remember, we have the voltage and current. We have the voltage current defined in the passive convention, right? So we have VT, we have IT defined in this way. And so this is circuit, this is circuit or the sub-circuit or whatever. So in this case, I would like to see what if the IT is equal just the sinusoidal steady state cosine omega t, but I also give it a phase angle, let's call it theta sub I. And Vt is equal V, the amplitude, times cosine omega t plus theta V. So the instantaneous power is the power. Now we are following the passive sign convention. Therefore, the power delivered to the circuit, the instantaneous power delivered to the circuit is PT. That's equal V times I, right? So the same thing as we did for all the other elements, but now we are kind of have a more general case. So if we substitute this V and I here, and we just get a V times V sub A times I sub A, and times the two cosine functions, cosine omega t plus theta V, and times the cosine omega t plus theta I. Now I would like to bring the trigger identity. By the way, if you're still not owning the trigger identities, I strongly encourage you to watch the Appendix B in this YouTube playlist. And so in this case that I am going to use the trigger identity cosine x times cosine y. That's going to be equal half cosine x plus y plus cosine x minus y. Okay. Actually, the first trigger identity without the memorization, okay, is how I got the trigger identity for this term and for this term. If you add these two, you get a 2 times cosine x cosine y. Right. So therefore, cosine x cosine y is half of that. But in the case, so the PT with that trigger identity, I would have. So now, of course, you can think about this as x, think about this as y. Doesn't really matter which one is x, which one is y. So in this case, I would like to have half v sub a I sub a times cosine x plus y, which is 2 omega cosine 2 omega t, right? Cosine 2 omega t plus theta v plus theta I, right? And the second term, cosine x minus y, would get plus cosine theta v minus theta I, because cosine omega t, in that case, omega t minus omega t, they are canceled. And now, for steady state, we know these are going to be constant for steady state, right? For steady state, and some of you asked the question by posting comments on YouTube, and that means all I sub a omega theta I, v sub a omega theta v, all these are constants. They don't change, okay? They don't change over time. So you see these, we will have two terms, right? So we will have half VAIA times cosine theta v minus theta I. Since theta v and theta I are constants, so therefore this is going to be a DC term, right? And also we have another term which have VA times IA times cosine 2 omega t and plus theta v plus theta I. So this is a 2 omega term, so this is an AC term. This is 2 omega AC term. If you use one capital, that's fine. Actually, there are two conventions, right? AC using lowercase or using capital uppercase. So two things, right? Two things I want to mention here for this general case. So that the DC term only exists if it's non-zero. So the DC term, this is non-zero if theta v minus theta I is not equal to plus 90 degrees, right? So if they're 90 degrees or negative 90 degrees, then you get zero. So that's actually what happens for the inductor and the capacitor case, right? And the AC term always there, right? The AC term always there. So another thing is, here we have the current and voltage in the same frequency, right? So what if they're not in the same frequency? If you follow what we did here, let's see, if you don't have it the same frequency, let's say the current has one frequency, the voltage has another frequency. Hey, you may wonder why we have that case. We will. If you take 425 or other courses, you may have a non-sinusoidal voltages or currents. And in that case, if we later this course, we're going to do Fourier series. So you're going to have these cross terms, the product of the voltage in one frequency and the current in another frequency. So in that case, the instantaneous power due to those terms will be only having the AC term. There would be no DC term in that case, right? So that's the thing I want to bring to your attention. And let's look at the Google Colab notes. And I already read the code. Here I just give you a kind of intuitive view of what this what this instantaneous power looks like. So here we have, I hope so I don't know if you can, this computation gonna record my cursor, I doubt. So here we have the voltage, right? So we have the voltage, like 10 volts in the cosine function, right? The current here, I have also cosine function, but also I have a way to change the phase angle. So now the voltage, the current, the current IT now has 30 degrees phase angle leading this this voltage. So that's at 30 degrees. So if I change that to 0, I believe that will make them in phase. Let's see. Yes. So if I change 0, you see they cross and same, right? So in this case, this were for the resistance case. Then you have a DC term, right? So the blue line, I'm plotting this instantaneous power PT. The blue line in the lower panel here, that's the instantaneous power, the two terms, the DC term, which is the green term, and the pure AC term, kind of the orange color. That's the 2 omega AC term, right? These two add up to the blue one. And if you have let's see, if we have inductance, for inductance, which one is leading which? For inductance, since the V is equal L di dt, so the V is leading the I by 90 degrees. So in this case, let's see, the current is lagging this V by 90. So I put negative 90 degrees there. Let's see, I put negative and see, yeah, so this is going to be, yeah, the current now is lagging this voltage by 90 degrees. You see, the instantaneous power, actually these two, the blue line and the orange line I used to have, actually they coincide with each other. So the 2 omega term now, the DC, the blue one, there's the DC term is gone, right? There's no DC term anymore because there's no, that's why you take the average power for the inductors would be 0. Let's look at the capacitor case. Capacitor case, in that case, since the I equals C dV dt, so the I is leading the voltage by 90 degrees. Let's see if I can change that to plus 90. Let me bring the keyboard. So if I just delete this angles, now the current leading, you see this current here is actually reaches the peak 90 degrees before the voltage does. So in this case, again here, the blue line, the green line, which is the DC term, is 0, straight constant 0, and also the blue line and the green line, the orange line. The blue line, remember, that's the total, the DC plus the 2 omega AC. Right now, the DC term is 0, so therefore, the 2 omega AC term is equal total instantaneous power PT. Okay, that's what I wanted to share with you. This video is recorded on a different day from the 3 video clips I already recorded, but this is a bonus one. Okay, until next time, keep, if you do whatever you're doing, just keep going and never stop, right? So see you next time.